In this video, we're going to continue with glycolysis, and we're going to start right where we left off with reaction 3, which is phosphofructokinase, PFK, phosphorylating fructose 6-phosphate, F6P, to fructose 1,6-bisphosphate, FBP or F16P. So here we are, fructose 6-phosphate, ATP. Magnesium is your cofactor, going to FBP, ADP, and H+. Note, this is a bisphosphate and not a diphosphate. A diphosphate is when you have your phosphates linked together. Like in ADP, you have phosphate linked to another phosphate. In bisphosphate, you have two phosphates. They're just linked to something else. And this is actually very similar to the hexokinase reaction that we looked back in the previous steps of glycolysis, in that we have magnesium, and that's shielding the negative charges of ATP, allowing for carbon 1 OH to make an attack. Previously, we were looking at carbon 6 making an attack. And reaction 3 is one of the rate determining steps of glycolysis, which, if you remember back from our previous videos, means this is going to be one of our slowest steps. And so we can inhibit this step to either speed up the flow or slow down the flow of glycolysis. So PFK is enhanced with AMP, which makes sense. AMP means you are low in energy. So you want to burn glucose to get more energy. So AMP will speed this up. While if you have ATP, if you have a lot of ATP around, this will actually slow down this reaction. It will inhibit PFK, which again makes sense. If you have a lot of ATP around, you don't want to break down glucose and make more ATP. It's also inhibited by citrate. Citrate is found in the citric acid cycle. So this is also a signal saying you have a lot of energy. So stop breaking down glucose and store it instead. So reaction 4 is we take our fructose 1,6-bisphosphate and we're going to cleave it. And we cleave it into 2 3-carbon molecules. DHAP, dihydroxyacetone phosphate, and GAP, glyceraldehyde 3-phosphate. And the enzyme that is going to do this for us is atolase. Note, when we do this, the numbering of our atoms now become a little weird. So fructose 1,6-bisphosphate, atom 1, 2, and 3 are corresponding to atoms 3, 2, and 1 in DHAP. So atom 1 becomes atom 3 of DHAP. Atom 2 stays the same. Atom 3 of our glycose becomes atom 1 of DHAP. Atoms 4, 5, and 6 are now atoms 1, 2, and 3 of GAP. And this is an aldol cleavage, so it's going to go through the mechanism of base catalysis, bond cleavage, enolate intermediate, and this intermediate has some resonance structure that can help stabilize it, and then some protonation to get our two products. So we're going to look at the mechanism for this now. So here's our enzyme pocket. Our two main amino acids for this are lysine 229 and aspartic acid 33. So step 1, substrate binding. You have your fructose 1,6-bisphosphate coming in and binding. Notice that carbon 4 is hydrogen bonding with aspartic acid, which leaves the carbonyl carbon facing our lysine. So our step 2 is that our substrate, FBP, will react with the amino group of lysine to form our iminium cation and our protonated shift base. So here we go here. During the process, we actually lose water, as we see that this carbon now forms a double bond with our nitrogen of lysine. And we also have a hydrogen bond stabilization still happening between asp and our sugar here. And what actually happens now is that our aspartic acid will take the hydrogen off of carbon 4. This will allow our oxygen that was on carbon 4 to form a double bond with our carbon then the bond between carbon 3 and carbon 4 are now broken. So you will form your intermediate, your N-anamine intermediate that we talked about on the previous slide at step 3 here. So during step 3, you have your bond breaking of your glucose and you get one of your products, glyceraldehyde 3-phosphate. And now you have your intermediate that is still linked to our enzyme. So we need to get rid of that because we remember for every enzyme we need to go back to where we started from. So we have this aspartic acid that is protonated. That's going to give the hydrogen right back to these double bonded carbons. So that happens and our intermediate is now broken down and we are back to a protonated Schiff base. If you look between step 4 and step 2, the Schiff base actually looks the same. The only thing that's different now is that you lost 3 carbons. Otherwise, you're back to where you are at step 2 here. Water comes in. That's going to cut away our lysine here and form a carbonyl carbon, reprotonating our lysine. So we have hydrolysis of our cation. So we are releasing DHAP now, and we have the free enzyme ready to go again. So those are the 5 steps of catalase. Reaction 5, we have to convert DHAP to GAP. The reason is, as you saw in the previous mechanism, you get 2 different 3-carbon sugars. To be efficient, though, we only have enzymes that work on one of these 3-carbon sugars, and that's GAP. So only GAP continues along the metabolic pathway. And so triose phosphate isomerase, TIM, which makes sense, is working on triose phosphates, which is DHAP and glyceraldehyde 3-phosphate, and you're just isomerizing or changing them. Here we have N-diol being our intermediate. So here's our intermediate, and then we just have our conversion where you're just moving the C double bond O all the way from carbon 1 to carbon 2. That's all TIM's doing. And after reaction 5, we are done with the first phase of glycolysis, that is putting in energy. So just to recap, we took glucose, added ATP to make G6P, did isomerization make F6P, added another ATP to make FBP, split this FBP in 2 to make GAP and DHAP, then converted our DHAP to GAP. So far, 2 ATP have gone in, no energy has come out. So let's start getting into how we get energy out. So we're going to start with phase 2 now. Phase 2 begins with reaction 6, where you have oxidation and phosphorylation of our GAP by NAD plus and phosphate. The enzyme that is going to catalyze this is glyceraldehyde 3-phosphate dehydrogenase, GAPDH. So what's happening here? You see our glyceraldehyde 3-phosphate, add NAD plus a phosphate, you're adding a phosphate to carbon 1 while making NADH. And the reason why this reaction goes through is that this aldehyde oxidation, through this oxidation, this is very exergonic, that is negative free energy. So this is driving the synthesis of 1,3-bis phosphoglycerate. And while you're doing that, you're also making NADH, which in itself is an energy storage that will be used in oxidative phosphorylation. So here in our first step, we created a high energy acyl phosphate, which is good. We also created NADH, which we can use for energy later. So already in reaction 6, we're starting to get some payoffs. So let's take a look at this mechanism. So here, the first step is that we're going to have our GAP bind to our enzyme, as shown here. Next is an important sulfyl group will attack the aldehyde. And we're going to have a base take the hydrogen away from our sulfur, a sulfhydryl group. That sulfur is going to attack the carbon of this carbonyl carbon, forcing this oxygen to be negative. And this is a thiol-hemal acetal intermediate. We looked at hemiacetals during our sugar chapter in Biochemistry 1. And we're doing the same thing here, but instead we now have a sulfur connected to a carbon and an oxygen. You can see we have a cofactor here, NAD+, that is just hanging out on the site. So since we have a negative oxygen, we're going to try and make that non-negative. So NAD is going to take our hydrogen from carbon, and then we're going to form a carbonyl carbon now. This is our acyl thiol ester intermediate. See, we have an acyl and a thiol ester here, and we have NADH. So the next thing is phosphate is going to bind, and this phosphate is going to attack this carbonyl carbon. That will allow our sulfhydryl group to retake the hydrogen from this base, restoring the base, and we're going to get 1,3-bis-phosphate glycerate out. So our product is ready to go. It's no longer attached to our enzyme here. NADH now can leave as well, and we have to bring in a NAD+ to restore the enzyme. Our enzyme is ready to go, and we can restart all over again. So we have this high energy mixed anhydride. We made NADH, so everything's going good so far. And we're going to continue with phase 2 of glycolysis in the next video, so I will see you there.